Hey everybody, let's talk about some graphs. This is going to be super exciting. All right, so let's talk about ways to look at graphs, and there's three particular ways that we can look at graphs. The first way is the coordinate method. I don't like this grid, so go away. All right, here we go. The slope is the second way, and the area under the curve. Okay, so the purpose of this video is to dive back into say, what did these things mean? Why are you saying them all the time? So how do I do them? So this is a chance for us to revisit those kinds of things. So really it is a way to analyze graphs. We have to get away from this idea that graphs are just this thing that you look at and immediately understand. We're going to analyze them. There's going to be a process, and here are three of the ways. So we're going to do that by looking at three of the same graphs, velocity versus time graphs, and they're going to have all the same functions on them. The first one here is the coordinate method. It's the one you learned in kindergarten. And so we're able to read kind of just seeing what happens. So the velocity is like going up, right? So you can look at it and say, okay, at a particular T1, this is what the V1 is, but you see that as time goes on, the velocity is increasing, right? Because the time is increasing, so that we can just see that. So it's easy for us to look at this graph and say the velocity is increasing, blah, 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 blah. Okay, we understand this methodology better than any other, all right? So I guess I can expand upon that and say, as we go from 1 second to 2 second to 3 second to 4 second, the velocity is growing up from 2 to 4 to 6. Okay, it doesn't matter what the units are. Again, we're trying to do this qualitatively. But this is the idea. This is the way that you have been programmed to think about graphs. And we're pretty good at it. So we can really just look here and say, like, what is the y-axis doing as we change the x? And so the information that we're going to get from the so-called coordinate method is just whatever is on the y-axis. Okay? The second methodology that we're going to look at in this second graph is the slope. We're familiar with the slope. It's a delta y over delta x. Although I think in math you say y2 minus a y1 over an x2 minus an x1, but whatever. So when we're looking at the slope, we need to figure out what the slope of that particular graph means. Okay, so we say, what does the y value equal? Well, in this case, it equals v. What does the x value equal? In this case, it equals t. So then we say to ourselves, what does v divided by t equal? So we look in our reference table, we find an equation, and we say it's acceleration. So now we know that when we describe the slope, we are describing the acceleration. Okay, that's the point. We need to know that. And then we have those categories of the ways that we can describe the slope so that we can get to the next thing. Okay, area under the curve is the one that people are the most like, yo, what about? All right, and I usually abbreviate it to AUC, area under the curve. Let's just slide those together, bring the U over, just slide it over, and the C over, and then, okay, there we go. All right, so area is a base times a height. And depending upon the shape of the base times the height business, we can say it's a triangle. So that's 1/2 base times the height business, okay? We could do rectangles. We could do, a rectangle and a triangle, which would be a trapezoid, but I would split it up. Okay, so the idea is we're going to have the area between the function and the axes. So in this case, you see it's a triangle. So in this case, we would use 1/2 base times height. So what does that equal? Really what we're asking ourselves is, yes, it's a triangle. Thank you, past Mr. Ross. Okay, so what does velocity times time equal? Right, because the base times the height is the base is the x and the height is the y. So what does base times height equal? All right, now you can get the information for actually physically actually calculating this by reading it off the graph and saying the height of the triangle is, right, and the base of the triangle is. Okay, so this is back to what I was saying a second ago. The time times the velocity is the base times the height. So what does that equal? So again, we go to our reference table to try to find an equation. Well, you could use units, I suppose, but the equation that we would find in the reference table is v equals d over t. All right, how do we make that look like v times t equals d? Well, we multiply both sides by t, we get rid of that, and we're left with vt is equal to d, so we know it's displacement or distance depending upon what the information given is, whether it's velocity or speed. So these are in general the three ways the three things that we can look at in this graph. All right, so these are all velocity versus time graphs, and here we go. This is a more generalized look. So in general, step one is the coordinate method. It's whatever is going on the y-axis. Whatever that y-axis says is what that is equal to. Step two, or option two, is the slope. You say, if I divide the y by the x, what quantity does that equal? And then step three is area under the curve. So if I multiply the y times the x, what quantity does that equal? And this is how we are going to analyze all graphs.
And now for something completely different.
It's a dog with a face. It has a face. The dog has a face. So let's take a look at this honey badger example. Okay, honey badger, gracefully prancing in a negative direction at a constant velocity. Pretty exciting stuff. Okay, so you see under this displacement versus time graph, I have the three ways that we can look at the graphs. The y-axis on that graph is displacement. The slope is the d divided by the t, the y divided by the x, and that's equal to the velocity. Okay, and the base times the height is equal to nothing. Distance times time is not a thing. All right, so now let's look at the next one. The y-axis is the velocity. What about the slope? It's the y, that's the v, divided by the x, that's the t. What does that equal? Just like in when we were going over before, that's acceleration. All right, so what about the area under the curve? Well, the base is the time, the height is the v, so it's v times t, so that's equal to the displacement. So the area under the curve is displacement. Notice it's different, all right? So the y-axis on one is not necessarily the y-axis on the other, and the slope on one is not necessarily the slope on the other. They're different because we have different y-axis values, okay? So on this last graph, the y-axis is the acceleration, the y is the acceleration, so that's an A, and it's an A over T, and that's a jerk. We don't really talk about the jerk in here. It means it's changing acceleration, so that cross calculus, so that's a no-no. Area, base times height, velocity times time, right, because of where they are. Oh, yeah, acceleration times time, mistake. Anyway, it's equal to the average velocity. That's what we get under there. Okay, so in this actual question, I recommend you start with the velocity versus time graph. That's the safe thing. We understand it the best. It's the easiest one in my experience for us to start with. Because this is moving in a negative direction, it means we need to be in this quadrant right here, right? Because this is the negative quadrant. This is the positive quadrant. So that means our line must be in that quadrant because it does have a negative velocity, okay? It also says that the velocity is constant. All right, that means the velocity itself shouldn't be changing. Where is the velocity on this graph? It is in the y-axis. So that means the y value must not change, which means a horizontal line is what we're looking for. Okay, velocity versus time graph, done. Now, the next graph, where is velocity connected to that graph? Well, it's connected by the slope on a distance versus time graph. All right, so we describe the velocity on the velocity versus time graph, and then we are describing the slope on the distance versus time graph, okay? So the slope must be, the slope on the distance versus time graph must be constant and negative because the velocity is constant and negative, and here we have three options that show us a constant negative slope. Constant meaning straight, all right? And those things must match. So if your velocity is 5 meters per second, your slope has to be 5 meters per second. If it's negative 15 meters per second, it has to be negative 15 meters per second. It does not matter where you start that line. It just matters that it has the right shape. In this case, constant and negative. Other than that, we're good to go with either one of these three, so long as the shape matches. Okay, now on to the last graph. So looking back at the velocity versus time graph, the slope of this graph now is the acceleration, and the slope is 0, which means we get a 0 value on that acceleration versus time graph. And we are all done with an example. Hope this was helpful. Goodbye.